Ever wondered what makes water flow? Let's find out together. Welcome to Fluid Mechanics 2, brought to you by CED Engineering Academy. Our guide, the renowned Prof. Dr. Alamgir Khalil from UET Peshawar. Known globally as the king of fluid and hydraulics, he's ready to take you on an educational journey like no other. Join us, master the mechanics, and transform your career. Subscribe now for more.
Okay, Bismillah Rahman Rahim. So today is lecture number 14. We will continue study about hydraulic machinery. In today's chapter, we will cover turbines. Now, before we start this chapter, the learning objectives for this chapter. After completing this chapter, you should be able to identify various types of turbines and understand how they work. So just like we studied about pumps in the previous lecture, in this class, we will study about the other important category of hydraulic machinery, that is turbines. So we will study what is a turbine, what are the different types of turbines, and we will understand how they work. You will be able to perform basic vector analysis of the flow into and out of turbines. So as we studied for case of pumps, similarly, we will study about how the fluid enters into the turbine, how the energy is taken in this case from the moving fluid, and the turbines we will be able to calculate, for example, the efficiency, that what is the output and what is the input to the turbine. You will also be able to use specific speed for preliminary design and selection of turbines. We studied about the specific speed in the previous lecture. The same concept applies for turbines, and using this concept we can do the preliminary design and selection of turbines because it tells us about the type of turbine. So after completing this chapter, you should be able to understand and answer all these questions related to these various topics. Before we start the turbines in detail, we already know that there are two broad categories of turbo machinery. As you see that in turbo machinery, there is a rotating element which we call it as a rotor. Rotor is a general name, clear? So that rotor in case of pump, that is known as impeller, as we studied, and the same rotor in case of turbine, that is known as runner. So we have two broad categories. The first one is pumps and the second one turbines. So we already covered pumps in the previous lecture. We already know that a pump supplies energy to a fluid. So you can see that we have this input energy and output energy of the moving fluid. So you see that because the pump, it adds the energy, so that's why the outflow energy of the fluid that is greater than the inflow energy. So what we say is that the purpose of a pump is to add energy, to a fluid, resulting in an increase in fluid pressure, not necessarily an increase of fluid speed across the pump. So pump basically adds the energy. That's why we are able to lift the water from one elevation to another elevation. On the other side, the turbine, so the turbine, it takes the energy, or we can say that turbine, it attracts the energy from a moving fluid. So a turbine, it extracts energy from a fluid. It means that the fluid enters into a turbine, and after it passes through the turbine, the outflow energy, that will be less than the inflow energy. So because the energy is extracted, so that's why you see that the outflow energy in case of turbine, that is less than the inflow energy of the fluid. So essentially pumps and turbines, they are the opposite. Their working is the opposite. Pump, it converts mechanical energy into hydraulic energy, whereas turbine converts hydraulic energy into mechanical energy. So for a turbine, we say that the purpose of a turbine is to extract energy from a fluid, resulting in a decrease of fluid pressure, not necessarily a decrease of fluid speed across the turbine. So this is the very broad and basic difference between the two broad categories of turbo machinery. With this understanding, now we start with the turbines. So you already know that what is a turbine. So the very broad types of turbines that are in use, we have water turbines, or we call it as hydraulic turbines, because these are water driven. So you can see here we have the rotating element, this shown here green in these figures. So the jet of water that is acting on this wheel, and it rotates the wheel. and the wheel takes the energy in the form of this rotating shaft. So it converted this hydraulic energy into mechanical energy in the form of this rotating shaft. Clear? So because it is driven by water, so we call it as water turbine or hydraulic turbine. Clear? Similarly, we also have steam turbine, where a steam is used, and with the help of nozzle, that steam, it rotates the bladed wheel, and this is how the energy is converted into mechanical energy in the form of rotating shaft. So because steam is used to drive this turbine, so it is known as steam turbine. Clear? Similarly, we have gas turbines. Clear? You can see here that we have air inlet that passes through a compressor here. It compresses, and then we have a fuel inlet, and then this is the combustion chamber, and as a result of this, you see here when it passes, so this is the rotor. Rotor means the rotating element, and this is how it rotates the shaft. So the energy is converted into mechanical energy. Clear? So now you can see that we have different types of turbines also today, nowadays, that we are using wind turbines. In this case, you can see that the wind, when it passes through the blades of this turbine, it will rotate these blades, and this is how the wind energy that will be converted into mechanical energy, and we are able to produce electricity. So we have different types of turbines, but primarily we will be focusing on water turbines. Civil engineers, they are more concerned with hydraulic turbines. That's why in this course, the type of turbines that we will study in detail, those are hydraulic turbines or water turbines. Clear? Because water driven. Now, why we are interested in water driven turbines? So in this case, you can see that we have a powerhouse. We are generating electricity from flowing water. So we have a head pond, or we can say a reservoir or a water storage. From there, we supply the water. This is known as the penstock. This is known as the penstock. So the penstock, as I said before, penstock actually originally was the name of a valve, but later on this whole pipe was then named as penstock. So penstock is a pipe or a tunnel through which the water is supplied to the turbine. So you can see that this water comes here. It is supplied through the turbine through this penstock, and as this water passes through this turbine, it rotates the vanes or blades of the turbine. So as this rotates, it rotates the shaft. So this hydraulic energy, it is converted into mechanical energy in the form of rotating shaft. And then this rotating shaft, it is connected with a generator. And generator converts this mechanical energy into electrical energy, which is provided to a community, to the national grid, for different purposes. As you already know, electricity we are using for different purposes. So this water, after passing through the turbine, it flows through this pipe in this case, which is known as the draft tube, and then it joins the tail race, the downstream water. So as you can see that this turbine, it is an essential component of the powerhouse. That's why we need to study and understand about the turbines. This is another diagram. We have a hydropower plant shown here. You see that we have a reservoir. This is a dam, and from the reservoir we have these tunnels, which we call it as the penstock. So the penstock, it supplies the water to the turbine, and as it passes through the turbine, it rotates the turbine, and then the water, it joins the tail race or downstream of the water. So when it rotates the blades of the turbine, then the turbine rotates the shaft. Clear? It rotates this shaft here, which is provided. So this shaft, it drives the generator. It drives the generator, and generator converts this mechanical energy into electrical energy. Then that energy is supplied through these power lines for different usages. So now you can see that in a powerhouse, this turbine is an important component. So that's why we need to study about the turbines, because you already know that why we have this powerhouse, because you already know that in Pakistan we have dams, and in dams we are generating electricity, the hydropower. So that's why this turbine, it is important component of the powerhouse. So we need to understand that what is a turbine, how it works. Clear? To further highlight the importance of study about the turbines, so we have the hydroelectric power. As you know that electricity we are generating from different sources. It can be from wind, but wind concept is not very common in Pakistan, although it is very common in the Europe and in US. So that is not very common concept. We do not have the complete technology to develop that to the fullest. Also that will depend that we have strong winds flowing across so that the turbine can work. Similarly, we are using the coal, that is thermal power, or we are using the furnace oil, etc. to generate the electricity. But you already know that that is more expensive, and the thing is that that is releasing hazardous gases into the atmosphere. So that is a health hazard. So that's why this hydroelectric power is not only a cheap source of electricity, but it is very environmentally friendly, because we are just using the head of water available to generate the power. And also the water is available for different purposes. It's not that it eats the water. No, it just passes through the turbine, and the same water is available for using different purposes. Clear? So you can see the importance of hydropower. The countries that produce the most hydroelectric power, you can see the comparison of the countries. They are producing the most hydroelectric power. You see China is on top. China is using this hydropower the most in the world. Clear? You can see the figures. These are in billion kilowatt hours, followed by Brazil and then Canada and so on. Now coming to hydropower in Pakistan. So straddling the Indus Valley, because you see Pakistan is spread over this Indus Valley. That's why we have the Indus Basin, the Indus River, that is a lifeline for Pakistan, supplying water for different purposes. So Pakistan is endowed with considerable water resources. According to the Pakistan's Water and Power Development Authority, WAPDA, which we call it as WAPDA, Water and Power Development Authority, there is 60,000 megawatt of hydropower potential in the country. So it means that in Pakistan, we can generate up to 60,000 megawatt of electricity from the available water resources, of which only 7,320 megawatt has been developed. This is the last year report, International Hydropower Association 2019 report, if you see. So it means that in Pakistan, there is a potential of 60,000 megawatt of electricity. But unfortunately, how much we are generating? Only 7,000. But now you see that the government that in the last few years is focusing on these hydro power generation in Pakistan, and not only extensions are done in the major dams. For example, you might have seen or heard or read in the news that we are extending the hydropower generation capacity of the Turbine Dam. Clear? So besides that, the government is developing small and medium-sized hydropower projects, because it is a cheap source of electricity, environmentally friendly, and the other purpose is to meet the electricity demand, because you already know that Pakistan is facing energy crisis. So only 7,000, just more above 7,000 megawatt we are generating of the available potential 60,000 megawatt of hydropower potential. So from where this hydropower is generated, so hydro capacity in operation included major plants at Turbine. So at Turbine, the initial capacity was how much? 3,478 megawatt. The Ghazi Barota, which is not a dam, but it is just a channel which runs from Ghazi to Barota. The head is available that we are utilizing to generate the hydropower, and it is providing us 1,450 megawatt of electricity. And the other major reservoir, that is the Mangla Dam, so generating about 1,000 megawatt of hydropower. These are the major plants. Besides, we have medium and small size hydropower plants. So in Pakistan, after the Turbine Dam, which was completed in 1977, we have not constructed any major dam. And you already know that dams are very important for us. Not only dams, they can generate the hydropower, but dams can store the water that you can use for water supply, for irrigation purposes, for agriculture purposes. And also, these dams can help in flood control, because if flood comes, you can store that water here and protect the communities. But unfortunately, unlike other countries in the world, we did not develop dams, which are very important for not only economy, but survival of the countries. So the province-wise installed hydropower generation capacity, you can see here that this is as per this report here, which is available online. You can see this report online. we have organization, you can say that is the PPIB, that is Private Power and Infrastructure Board. You can go to the website, it is a government organization, that's why you see gov.pk. So there you can see their annual reports, and you will find a lot of information about hydropower in Pakistan. So in that source, we can see that Khyber Pakhtunkhwa, it is contributing around 57% of the hydropower generation capacity. Gilgit-Baltistan is contributing nearly 2%. Azad Jammu and Kashmir, that is contributing 15.46% exact. And Punjab is contributing around 25%. This is the province-wise installed hydropower generation capacity. So you can see that very small amount we are generating out of the available 60,000 megawatt of hydropower potential in the country. Now, as per this report here, electricity production from hydroelectric sources, clear, percentage of total in Pakistan was 29.84% as of 2014. This is according to this source. Around just 30% of the total, clear, hydroelectric sources percentage of total, that was just 30% as of 2014. Its highest value over the past 43 years was 60% in 1978. So it means that in 1977, when we completed the Turbine Dam, so at that time in 1978, the contribution of hydroelectric sources was 60%. It means 60% of the electricity was coming from hydropower. But then over the years, we could not develop the hydropower plants, and the government focus was on thermal power, that is power generation from coal, furnace oil, etc. So that's why you see that the percentage was reduced to 30% in 2014. But now, as you know that furnace oil is expensive because the electricity you will sell with high price, and the thermal coal, these are not environmental friendly. So that's why now the focus is more on hydropower recently, and that's why you see that the government is developing a large number of small to medium sized hydroelectric power projects, clear, throughout Pakistan, because it is a cheap source of electricity and also environmentally friendly. So you see that even in 2000 it was 25, around 25%. But anyhow, recently this percentage, if you search on the internet, so it will be not more than 35%. After 2014, in 6 years, we just added 5% more here. So still it is not more than 35%. It will be around 35%. According to this report here, which is mentioned, you can study about more detail of existing hydropower projects in operation in Pakistan. So these are the existing. Those under development, you can find the latest information from the website. So those which are working under WAPDA responsibility, that is the Turbine Dam, that is located on the Indus River. The province is Khyber Pakhtunkhwa, and generating capacity is 3478. Similarly, the Warsak Dam, it is located on the Kabul River, located in province of Khyber Pakhtunkhwa, and the capacity is 240 megawatt. Similarly, we have this category of SHIDO. This is Sarhad Hydel Power Development Organization. Now its name is changed because the change name of our province, but previously it was called SHIDO, Sarhad Hydel Power Development Organization. They are responsible for these existing projects and possibly developing other as per latest information. Similarly, we have the Hydropower Energy Board, Azad Jammu and Kashmir. So they are behind these existing projects, clear, in Azad Jammu and Kashmir. And also we have the Water and Power Development that is related to Gilgit-Baltistan. So in Gilgit-Baltistan, these are the existing hydropower projects. So the total capacity is around 6,720 megawatt. Recently, you can find latest information from the website of PPIB. So you can see the importance of this, and because civil engineers will be involved in the construction and working of these hydropower plants, that's why we need to study about the turbines. So hydraulic turbines or water turbines that are driven by water, that can be divided into two broad categories. We have two very broad categories. So the first one is impulse turbine. The first category is impulse turbine. And the second category is a reaction turbine. These are the two broad categories of hydraulic turbines. We will study in detail the working of the two types of turbines. A reaction turbine. Clear? So the very common example of impulse turbine, that is Pelton wheel. So Pelton wheel or Pelton turbine, you see that in this case we have a nozzle and it produces a high velocity jet. It strikes these vanes or buckets of the turbine, and as a result of this it rotates. And when it rotates, it is connected with the shaft and it rotates the shaft. And this is how the hydraulic energy is converted into mechanical energy. So you can see that because this turbine works due to the impulse of water, the velocity head. So that's why the wheel does not run full in water. You see, only the water is striking part of this wheel and it rotates. Whereas in case of reaction turbine, so the wheel runs full because the water will enter under pressure and flows over the vanes. And this is how the energy is transferred. But here you see in impulse turbine, the fluid enters the vanes or blades with kinetic energy. It is only under atmospheric pressure. So atmospheric pressure we consider that zero for analysis. So that's why mostly that is kinetic energy. But in this case, since the fluid enters into the vanes or blades under pressure, that's why the wheel runs full. It is underwater. Clear? It runs full of water and it rotates the vanes or blades of the turbine, and then the water joins the tail race. Clear? So that's why this is known as the reaction turbine, because the change in pressure takes place in the guide, these vanes, rotating vanes. Clear? We will study in detail the working of this, but this is the main difference between the two types of turbines. Clear? Because here in the nozzle the change in pressure takes place and the water that strikes the vanes or blades with kinetic energy. But here the change of pressure takes place as the water flows over the rotating vanes. That's why the wheel needs to be fully underwater. So that we known as a reaction turbine. That's why these impulse turbine, these are also known as velocity turbine. These are also sometimes known as velocity turbine. And because in the reaction turbine, the water flows under pressure and it rotates the rotor vanes. So that's why these are also known as pressure turbines. These reaction turbines, these are also you study in other books. These are also known as pressure turbines. So this reaction turbine, the very common example is Francis turbine. We will study in detail in today's lecture about the working of Francis turbine. And also we have the propeller turbine. So the very common example is Kaplan turbine. You see here the water enters and then the water flows along the axis of rotation. Clear? So the same concept as we studied in pumps, the flow can be radial along the radius. Clear? Because in Francis turbine it is radial flow. The flow occurs along the radius. In case of propeller turbine, you see here the flow is along the axis of rotation. So that's why this is axial flow. And we can also have a mixed flow turbine in which the flow will be partly radial, partly axial. Clear? So you can see that the turbines, they are broadly classified into impulse turbines and reaction turbines. Clear? We will study the working of both types of turbines in detail. So hydraulic turbines, you can see here before we start, this is the impulse wheel runner. This is the rotating element of the impulse turbine. This one here, which you saw here, this one, the rotating element. This you can see here in this diagram. So what will happen is that there will be a nozzle that will produce high velocity jet. That jet will act on these vanes or buckets, and as a result of this, this wheel will rotate. This wheel will rotate and it will rotate the shaft. There will be a shaft that is connected with this wheel, and as a result of that, this shaft will be rotated. And this is how this hydraulic energy is converted into mechanical energy in the form of rotating shaft. It will rotate this shaft of the generator. So you can see the size of this impulse turbine as compared to the size of the average person. And you see that the diameter of this runner, or the number of buckets, the size of buckets, so that is basically the design aspects of the impulse turbine. This is now a case of reaction turbine. We have the runner of the Francis turbine. So the water, it will enter here at the center. It will enter at the center. The wheel must run full in this case, and then it will rotate. You see here, it will, let's say, rotate these vanes or blades. These are the vanes or blades. And finally, it will be connected to at the center. It will be connected on the other side, you can say. So it will be connected with the shaft, and it will rotate the shaft. So this is how the water flows, and then the turbine, it converts that hydraulic energy into mechanical energy in the form of rotating shaft. So this is the runner of reaction turbine, Francis turbine. Clear? This is an example of Kaplan turbine, a propeller type. Clear? So a propeller type means that you see the water will come here through these guide vanes, the water will come here, and then the water will flow along the axis, and as it flows it will rotate these vanes or blades. Similarly, the water come here through the guide vanes, and then the water will flow along the axis of rotation. So we have axial flow, so it will rotate this like a fan, the ceiling fan that we have. So when it rotates, it pushes the air downward, clear, along the axis of rotation or parallel to the axis of rotation. So this is a propeller turbine. Clear? The common example is Kaplan turbine. Clear? So in this case, you see that when this rotates, you see here when this rotates, it will rotate this shaft, and this shaft, it will be connected with a generator. This will be connected with a generator. So what the turbine did is that it converted this energy of fluid, hydraulic energy, into mechanical energy in the form of rotating shaft. And then this generator will convert this mechanical energy into electrical energy. So now let us start in detail about the impulse turbines, then we will study about reaction turbines. So now you can see that the working of impulse turbine, the different components. So you see that we supply the water through a penstock, which is a pipe coming from a reservoir. So it will supply the water, and in the end of the penstock we have a nozzle. So nozzle, although you see it is not connected directly with this turbine, but it is considered as integral component of the nozzle. Why? Because in the nozzle, the pressure energy is converted into kinetic energy, and that's why a high speed of jet, it flows and it strikes the vanes or blades and it rotates the runner. Clear? So that's why, because the change of pressure takes place in one or more nozzles, then that's why this nozzle, it is considered as integral part of the Pelton wheel or Pelton turbine or impulse turbine. So this nozzle, it converts the pressure energy into kinetic energy, and a high speed of jet, it strikes these vanes or blades. So these are the vanes which are connected fixed on the periphery of this rotating wheel, which is known as a runner. So remember this rotating element, the general name is rotor. So the rotor, in case of pump, we call it as impeller. But the same rotor, in case of turbine, we call it as runner. So this is a runner. It rotates, clear, and it is connected with the shaft here. So as it rotates, it is rigidly connected with the shaft. It will rotate the shaft of generator. So this is the jet of water that strikes the vanes, and as a result, this is rotated. Now the wheel does not run full in case of impulse turbine. You see this water, after striking the vanes or blades, the water will come down, and it will join the tail water. And it will join the tail water. This water will continue to flow down. But still, for protection purposes and to prevent splashes of water, because it will strike these vanes or blade, it will produce splashes of water. To protect against that, this casing is provided. Just for protection purposes, this casing is provided. Otherwise, even if you do not have the casing, still the turbine will work. So this casing is just provided for protection purposes. Protection against the splashing of water, because high speed of jet will strike the vanes or blade. It will produce splashes of water. To protect against that, this casing is provided. The next thing is this spear or needle, which you can see here. So what is the purpose of this spear or needle? So remember that, as I said, that in case of powerhouses, sometimes the load on the turbine drops. This is the turbine. So it is rotating with a constant speed by the supply of water, and it is producing electricity with the help of this generator, correct? Now sometimes what happens that the load on the turbine drops. So it means that we have to reduce the speed of the turbine because the load drops. So we have to reduce the speed of the turbine. This is known as speed regulation. So in order to reduce the speed, you need to reduce the quantity of water supplied. How you can reduce the speed of rotation of this turbine? These are huge turbines. We do not have a button to stop it and to start it like this. So that's why you have to reduce the quantity of water supplied. That will reduce or control the speed of this turbine. So for this purpose, these control gates are provided. In case of reaction turbine, because the wheel run full. So these gates are provided to control the supply of water to the turbine, so that we can control the speed of the turbine. So this mechanism is known as governor. Governor is an arrangement that is provided to control the speed of the turbine. So this is known as governor. So that's why we study as governing of turbines. You will study a topic, governing of turbines. It means how you can control the speed of the turbine. What different arrangements we provide to control the speed of the turbine in case if the load on the turbine drops. So in case of reaction turbine, we provide these gates to control the flow of water to the turbine. But now in case of impulse turbine, we do not have this arrangement. So in case of impulse turbine, what we have is that we do not have the gates, clear, to supply the control of water, because this can be here and we can have another nozzle that can be here. Not only one, we can provide more than one nozzle. Similarly, another nozzle can strike here. So the water is supplied from different pipes. Similarly, there can be a fourth one which strikes here. This can be a fourth nozzle. So it means more than one nozzle can operate. So then in this case, we provide for impulse turbine a different governor. We do it by the help of this needle, spare or needle. So in the normal condition, the needle will be here. The needle will be here in the normal condition. So the water flows and it strikes and rotates the runner. But if we want to reduce the flow, we have to push this needle in the forward direction. So when we push the needle in the forward direction, it will reduce the flow area. So when this needle comes here, it will reduce the flow area, and then reduced quantity of water will strike this runner. So this is how we can control the speed of the turbine. So this arrangement is known as governor. In general, we call it as governor to control the speed of the turbine. But remember, this is not the only case. We can have different arrangements. For example, before I explain that, we call it as Pelton turbine. Why it is called a Pelton wheel or Pelton turbine? Because this turbine is named after Lester A. Pelton, an American engineer who developed it in the year 1880. So the very classical example of impulse turbine that is discussed in every book, that is the Pelton wheel or Pelton turbine. So this is named after this American engineer. He was a mining engineer who developed this. So that's why it is known as the Pelton wheel or Pelton turbine. Now in this case, as I said, this needle that we provide to control the quantity of water supplied to the turbine to control the speed, it's not the only arrangement. There can be different other possible arrangements. What could be that? If we do not have this spare, we can provide a jet deflector that will come here. This will be a jet deflector that will come here. You see, it can come here and this water will come here. It will fall down and reduced quantity will strike the vanes or blades. So this is how we can control the speed of the turbine. This can be a jet deflector. This arrangement we call it as jet deflector. So we deflect the jet so that reduced quantity of water can strike, and hence we can control the speed of turbine. This is a second arrangement. What could be a third arrangement? A third arrangement is that this nozzle itself can be deflected. Now it is this position, but the nozzle can be deflected in this position. So you see here the water will then flow in this direction, and this is how we can control the speed of the turbine. So this whole discussion, this comes under the topic governing of turbines, means how we can regulate the speed of the turbine and what are the different arrangements that are provided to control the speed of the turbine in case the load on the turbine drops. So this phenomena, this comes under the topic governing of turbines, and the arrangement which is provided for that purpose is that is known as governor. So I already explained the working of impulse turbine, Pelton wheel. Water from a reservoir flows through penstocks. The water will come through these penstocks. At the outlet of penstock, nozzle is fitted. So we have nozzle. Remember, nozzle is integral part of impulse turbine. You will see nozzle in all the impulse turbines. Nozzle converts hydraulic energy, that is the pressure energy of water, into kinetic energy. Water striking the nozzle is controlled using a spare. So as I already explained, this spare or needle, this controls the water. Water comes out as a jet from nozzle and strikes the buckets. So this jet of water comes out from the nozzle. It strikes these vanes or buckets. In case of impulse Pelton turbine, we call it as buckets, which are fixed on the periphery of a wheel. So these buckets, these are fixed on the periphery of the wheel, and this casing that is provided for protection purposes, casing is used to prevent splashing of water. So this is how the impulse turbine it works. Clear? Now that we know what is a turbine, what are the different types of turbines, and how the impulse turbine works, you see this is a very simple impulse turbine principle. We have the vanes or blades. And you see here, when you supply the air, so it will rotate these vanes or blades. This is what happens in case of impulse turbine. The water comes, they rotate this, and then at the center it is connected with a shaft, and as this wheel rotates, it will rotate this shaft of generator. And this is how, in case of the water turbine, the hydraulic energy is converted into mechanical energy. Now this, you can see the impulse turbines. This is the Pelton wheel in our powerhouse. So you see the jet of water that will come, that will rotate, clear? Here the jet of water, it will strike these vanes, and as a result these will rotate, and they will rotate this shaft, clear, of generator. So this is how these impulse turbines, they are provided in a powerhouse. You can see the size of the buckets. So the buckets, these are ellipsoidal buckets. See, look here, these are ellipsoidal buckets with a splitter in the middle. So it will divide the jet into two portions, and you can see the size of the buckets. So these are big. Now we want to calculate head on impulse turbine, because we talked that it converts hydraulic energy into mechanical energy. So now we are interested to calculate the head that is acting on the turbine. So if we can calculate that head, then we can calculate the power that is available to the turbine using this equation, clear? So all we need to know that how much head is acting on the impulse turbine. So now you can see that the head that is available, that is, you see, if I consider one point here and another point here, so the head that is available, that can be utilized by the turbine, that is the difference of the water level upstream and downstream. The water level in the forebay, the upstream, and in the tailwater, that is the gross head available. Now you know that out of this gross head, because the wheel does not run full, it has to be set above the tailwater. The wheel has to be set above the tailwater by some distance z. So it means this much head is lost. This much head is lost. This you cannot utilize because the wheel cannot be in water. So it has to be set above the water by some clearance distance. So it means that this head is lost. So from the gross head, this head is lost. This is the static head that is available to the turbine. Now out of this static head, you see that we have head losses in the system. You already know that in this penstock, the liquid will flow, the water will flow. So there will be friction losses associated with that. So we have the friction losses associated with that. So that's why the head that will be available will be this Y minus HL, the losses that we have. The head that is available. So what is the head then available? This PB by gamma plus VB square by 2G just upstream of this nozzle. Because upstream of the nozzle, we have the pressure head and the velocity head. After the water passes through the nozzle, this pressure head is converted into velocity head, because the water that is striking the vanes or the blades only with kinetic energy. So that's why we take the base of the nozzle. We consider the point upstream of this. So that's why we can consider PB by gamma and VB square by 2G. So the head that is available, the nozzle is considered as integral part of the impulse turbine. Hence the net head or effective head H, that is head at the base of the nozzle, is the static head minus the 5 friction losses. So Y minus HL, this static head here, minus the head loss, that is the head available to the turbine. This is what we shows that this is the power available to the turbine, gamma QH. This is the power available to the turbine. So for the net head available to the turbine, this H is equal to PB by gamma plus VB square by 2G, or the static head minus the head losses. So this is the head that is available to the turbine, and this head the turbine has to convert to mechanical energy. So this is the pressure head and the velocity head upstream of this nozzle point B. This is the net head that is available. This head multiplied by gamma Q, that is the power input to the turbine. So this power, if 100% converted into mechanical energy, shaft power, then the turbine will be 100% efficient. But since this is not the case, we have losses, as we studied in case of pumps also. So now let us see that what are those losses. But remember, this is the input head and this is the input power. Now let us see that what are the different losses in case of turbines and how this head is utilized by the turbine, clear? So the head or energy supplied at the base of nozzle, that is consumed in 4 ways. It says that this head that is consumed in 4 ways. How? Number 1, some energy is lost in fluid friction in the nozzle, known as the nozzle loss. This head which is available now, this head which is available, out of this energy, This is energy. Out of this energy, there will be, as the water passes through the nozzle, there will be nozzle loss, because you studied nozzles in detail in your fluid mechanics 1 course. So there will be a nozzle loss. Clear? Because the nozzle has a converging section, and we already studied the minor losses. When we have converging diverging section, losses are associated with that. Clear? So that will be called as nozzle loss. So it means out of this head available, some energy will be lost in the nozzle. See, before even entering the blades of the turbine, some head is lost. The second head loss is due to the friction of the fluid as it flows over the buckets. As the water will flow over the buckets, clear, there will be friction. We already studied about this in momentum and forces in fluid flow. So as the water flows over the buckets, there will be friction and some of the energy will be lost there. That's why the outlet velocity, relative velocity, you remember small velocity, we use small v, we use for relative velocity. You see the same concept we will use here. The capital velocity, the velocity of the jet of water, the absolute velocity u of the vane or blade, and then the relative velocity. That is the between these two, the relative velocity, because these are moving at different velocities. So the same concept we use here. So the relative velocity at outlet, that will be less than the relative velocity at inlet. This will be due to the friction over the buckets. And what is the third? Kinetic energy is carried away in the water discharge from buckets. So we say these are ellipsoidal buckets, as you saw the shape of the buckets. The water will strike at the center, and after the water strikes, the water will leave on both sides. This is the shape of the bucket of the Pelton wheel. The water will leave on both sides. You saw here. You can see here. The water will strike in the middle. The water will strike in the middle, and then it will flow over these buckets and leave in both directions. So it is split in two directions. This is how the water will flow. Clear here. So in this case, because the water flows with some velocity, so it means not all of the kinetic energy that is fully utilized. Because at the exit, the water still exits the buckets with small absolute velocity. Actually, the water is striking the buckets with kinetic energy. So the water should leave with zero velocity. In that case, the full kinetic energy will be transferred. But as the water exits with very small velocity, v2, the absolute velocity, so it means that not 100% of the kinetic energy that is supplied to the runner. So that is considered as a loss. So out of this head which is available, this head which is available, this energy which is available, these three are the losses. The nozzle loss, the friction over the buckets loss, and as the water leaves the buckets with small absolute velocity, that is a loss. The remaining, that will be the head transfer to the runner. Out of this head, if we subtract the three losses, that will be the head that will be transferred to the runner. That is head directly available to the buckets. So what we can write down, that this H which was available, this is the loss due to the nozzle. This is the loss due to the nozzle. You might have developed this equation in your fluid mechanics 1 course when you study about the nozzles. This is the head loss due to the nozzle. Also, we can express this as Kn, the nozzle loss coefficient Kn, into Vj, this Vj square by 2g. Vj is the velocity of the jet of water. We can also express this in this fashion. But anyhow, this is the formula that you might have studied in fluid mechanics 1. So this is this one. This one loss, it is expressed here. The two loss, that is expressed as here. The friction loss, as the water flows over the buckets. So it is expressed as K, the bucket loss coefficient, into V2 square by 2g, the relative velocity at exit. And the third one, because the water flows with a small absolute velocity, that is considered as a loss, which is here. So we have these three types of losses, that when you subtract from H, we get this H double dash. That is the head that is transferred to the runner. That is the head directly available to the buckets. Clear? We will see where is H dash. In the reaction turbine, I will show you where is H dash. So just to be consistent, we denote this with H double dash. So this H double dash remain the same for reaction turbine also. Clear? So you can ask a question that now from H we have H dash, why we write down H double dash? So when we study reaction turbine, I will show you the H dash. And then we have the head transfer to the runner is H double dash. So to be consistent with that, for impulse turbine, we directly use H double dash. Clear? So these are the various explanation of the different parameters that we write down here in this equation. Cv is the coefficient of velocity of the nozzle. Aj is the cross-sectional area of the jet. Ab is the cross-sectional area of the pipe. upstream of the nozzle, and so on. This K, this is known as the bucket loss coefficient. This is known as the bucket loss coefficient, and typical values vary from 0.2 to 0.6. So this is how we can, now that we have the losses, so we can now calculate the hydraulic efficiency of impulse turbine. What is the head available? This is the head available, but this is effectively transferred because of these losses. This is effectively transferred. So now we can define the hydraulic efficiency of impulse turbine. So the nozzle, it is considered as an integral part of the impulse turbine. The hydraulic efficiency, which is denoted by eta dash for impulse turbine, is power transferred directly to the turbine buckets divided by the power in the flow at the base of nozzle. So this was available to the turbine. This was available to the turbine that we studied here. This was available, gamma QH. This was available to the turbine. Because we have the three losses, so now that is actually transferred to the buckets. That is gamma QH double dash. So gamma Q cancel out. So the head that is actually transferred to the buckets divided by the head available to the buckets, that defines the hydraulic efficiency of the impulse turbine. Then we have the overall efficiency. So the overall efficiency, or simply efficiency of an impulse turbine, is less than hydraulic efficiency because of that part of energy delivered to the buckets that is lost in the mechanical friction in the bearings and windage. Because you know the wheel rotates, so there will be bearings, there will be mechanical friction, and also windage. Because the huge wheel rotates, there will be some air effect on that, wind effect. So it will further reduce the final output. It will further reduce the energy delivered to the shaft. So the overall efficiency, or simply the efficiency, that is the final output, which is the rotation of the shaft. So T omega, the final output divided by the initial input. The final output divided by the initial input, that is your overall efficiency for that machine. If you remember, in case of pump, it was gamma QH divided by T omega. But in case of turbine, it is T omega divided by gamma QH. That's why pumps and turbines, they are the opposite machines. Now this is the overall efficiency. So remember, in the 10th edition of the book, we just defined the overall efficiency mainly, or the hydraulic efficiency for impulse turbines. But if you study the 8th edition of the book, we have more efficiencies. We have the hydraulic efficiency, eta H. It is same as this, eta dash, in the 10th edition of the book. That is the head that is transferred to the buckets, divided by the head that is available to the buckets. So this is the hydraulic efficiency. Then we have the volumetric efficiency. It has to do with the discharge. What is the discharge available, and what is the discharge actually acting on the buckets? Because there could be some leakages. Some of the discharge can miss. May not be the case in impulse turbine, but you see in reaction turbine, the wheel runs full, so there can be some leakages. So due to that, we can then define the volumetric efficiency, that how much quantity of water is available and how much quantity of water is actually acting on the blades of the turbine. And then we have the mechanical efficiency, eta M. That is lost due to mechanical friction in the bearings in the machine. So the product of these three, that defines the overall efficiency. The final output divided by the initial input. So we can define the hydraulic efficiency, the volumetric efficiency, the mechanical efficiency, and the overall efficiency for turbines. Also for pumps. But now in the 10th edition, they no longer go into this much detail. So we just stick to overall efficiency for pumps and also overall efficiency for the turbines, which is the final output divided by the initial input. Now that we are able to calculate, we say that the power transferred. We talk about here that the power transferred. So now it means that how much force is acting as these water strikes the buckets, how much force is acting, and then how much power is transferred. This is what we studied in momentum and forces in fluid flow. So now we are interested to calculate the action of impulse turbine. As we saw that the buckets of the Pelton wheel, these are ellipsoidal buckets. You can see here, these are ellipsoidal buckets with a splitter in the middle. So that's why the jet, it will strike the buckets at the center, and then the water, it will be, the jet of water, it will be split into two. This is the absolute path. So that's why you see the absolute path, the absolute velocity. And it makes an angle of alpha 2 with u. U is the speed of these buckets. And because the water flows over these buckets, this is the relative path. This is the relative path. This is the relative path. So that's why this relative path, it is denoted by relative velocity. You see here, and this relative velocity, it makes an angle of beta 2 with u. So because the jet of water, it enters like this, you see, that's why the inlet velocity diagram is like this. This is the inlet velocity diagram. This you have to draw to calculate the forces, because we have to calculate compressible. Similarly, for flow can be uniform flow, it can be non-uniform flow. Similarly, the flow can be steady flow, the flow can be unsteady flow. We can have a steady uniform flow, we can have a steady non-uniform flow, we can have a steady laminar flow, can be a steady turbulent flow. Don't try to mix things that because laminar flow, we consider that the velocity profile is not changing in the x direction, it is a steady flow. Clear? So that's why in the beginning I told you that these are different concepts. Don't try to combine them. You already studied them in fluid mechanics 1. You studied about compressible, incompressible fluid. That is related to the density. If the density is constant, we say the fluid is incompressible. If the density is variable, the fluid is compressible. Then you cannot say that if the flow is steady, it should be compressible or it should be incompressible. So that's why in the beginning I clarified this concept that don't try to mix things. It doesn't mean that if a flow is steady, the flow will always be laminar or it will always be turbulent. I hope your question is clear.
तो सर इस प्रॉब्लम में हमने क्यों कहा है कि ये फ्लो लेमिनर होना चाहिए सर?
तो आपने ये जो इक्वेशन है किधर से निकाली है? ये जो आपके पास इक्वेशन आई है ये किधर से निकाली है?
ठीक है सर,
ये फिर आप किधर से निकालेंगे इक्वेशन है? आप ये तो नहीं कह सकते कि बस एक फार्मूला है मेरे पास और ना इसी एक फार्मूले से हम सब कुछ निकालेंगे और हर किस्म के प्रॉब्लम सॉल्व करेंगे। ऐसा तो नहीं हो सकता है। ये तो देखें अभी आपके पास क्या है कि ये इक्वेशन है हमारे पास, तो इस इक्वेशन में आपके पास हमेशा हम क्यू आई 0 लेंगे या कांस्टेंट लेंगे, तो क्यों लेंगे? ऑलरेडी मैंने बता दिया कि दिस क्यू आई कैन बी वेरिएबल। जब ये वेरिएबल होगा आप देखेंगे कि इस इक्वेशन को जब आप इवैल्यूएट करेंगे यू विल गेट कॉम्प्लेक्स इक्वेशंस बिकॉज यू आल्सो कंसीडर क्यू आई को हमने 0 किया, यू सी द इक्वेशन बिकम सिंप्लीफाइड। आप अभी क्यू आई को वेरिएबल ले लें, द सिचुएशन विल बी टोटली डिफरेंट। दिस वेरीज फ्रॉम केस टू केस। So you have to see the nature of the problem, that is the flow steady or unsteady? For the given case, is the flow uniform or non-uniform? For the given case, the fluid is compressible or incompressible? For the given case, the flow is laminar or turbulent? All you have to look from every prospect when we solve the problems. I hope it is now clear.
Yes sir, clear.
Okay, so let me quickly take this problem before I take a break. We need to cover more material. Now we have a variable tank now. In this case, now the discharge is occurring through an orifice here. This is the orifice at the bottom of this tank. So now in this case, we have a cone-shaped tank now. Now the AS is variable. Now it is not constant. You will see that it is now variable. We just consider a simple case here. So AS you can calculate. If it is circular, pi by 4d square, very easy. Now it is variable. So now you will see the problem becomes complex. Whatever, we have to learn how to solve them. So now the question is that we have this cone-shaped tank in the form of frustum of a cone. This is the area of the orifice here at the bottom, and the coefficient of discharge coefficient is given 0.60, and the diameter D1 is 12 meter. This is 12 meter. This is 12 meter. And this diameter D2 is given, it is 5.6 meter. And Z0 is given 10.4 meter. This is given as 10.4 meter. Now it says that how much time it will take for water level to drop from section 1 to section 2. How much time it will take? What is given is that the tank diameter, that is, let's say whatever, small d or capital D, their diameter is equal to k times y, where k is a constant. It means that the diameter is changing with respect to y. It is not constant. This is given in the question. So accordingly you will work. And y is equal to z plus h2. This is now given in the question. So now we have to solve the problem. For this given condition we have to put. Then you will say that why it is given k times y instead of ka is not written. So this is not a question. The question is you are given a situation and then accordingly you consider the situations and try to solve the problem. This is what we learn through these examples and practice of fluid mechanics or whatever mechanics you study. Clear? So now in this case, because the diameter is variable, so we have to calculate AS. What is the big problem here? The big problem is AS. In the equation now, AS is variable, QI is 0, AS is orifice. You have a simple formula. So now what is the biggest challenge in this question? How we calculate AS, which is now variable? If it was constant, very easy problem. So now how to calculate this? There are actually two approaches. I will teach you two approaches, how you can follow, up to you, which one you easily understand and easy for you, convenient for you, you can follow and solve the problem. So the first approach is that you can see that we can compare these similarity triangles that can form here. So H2 divided by Z0, this H2 divided by Z0, this is equal to D2 minus 0, but 0 not written, D2 divided by D1 minus D2. It says that this ratio is same as this ratio. This is how it is written. Left hand side is equal to the right hand side. So from here we can simplify. H2 is equal to D2 into Z0 divided by D1 minus D2. Now everything is known. Just plug in the value. So H2 is now 9.1 meter. And now we are given that this Y is equal to Z plus H2. What is Z? Z is essentially this distance. Y minus H2 will be your Z. And we have to express the area in terms of Z. Why? Because in the equation, what we have, in this equation, what we have, we talk about this dz. So if you want to evaluate the integral, you have to express the variables in terms of Z. That's why we are doing here. We have to now express this area in terms of Z now. So now your H2 is 9.1 meter. So now Y is Z plus H2. So Z is variable. So 9 plus 9.1. Now we are given that D is equal to K times Y. So D has to be expressed in terms of this Y here. But Y is now equal to Z plus 9.1. So what we can write down is that K is equal to D by Y. This is given by this values. K is a constant, 0.615. This is the change which is occurring. What is the change occurring in the diameter in 10.4? In 10.4, what is the change occurring? From 5.6 to 12. So what is the change occurring in 10.4? 12 minus 5.6. So it means that this equation is now equal to what? This is equal to D into 0.615 times Y. So now you change the Y, you change the diameter, and you can see here. But because we have to express this in terms of Z, not Y, so that's why in AS pi by 4 D square, D will be equal to 0.615 times Y, but now Y we have to replace by Z. So what you will do is that AS is equal to 0.297 into Z plus 9.1 whole square. So now your AS is expressed in terms of Z. So now DZ and Z here, we will be able to evaluate the integral to calculate the time for water level to come from 1 to 2. Now the question is easy. QI is 0 and Q naught, it is given by this simple formula for the orifice. Z is variable. So now you just put Q naught is a function of Z, and now we say AS. You put AS here and you put Q naught as here. QI is 0 and the water level drops. This total is 10.4 meter. This is 10.4 meter. This is 12 meter. And this is how much? 5.6 meter. So now you can see the integral is now complex. So you have to evaluate the water level comes from 10.4 to 0 here. 10.4 to 0. Just evaluate this integral and it will take 605 seconds for water level to come from 1 to 2. Divide by 60, you can calculate in minutes, whatever hours you are interested. So this was one approach to calculate the AS. If you are not convenient, there is another approach. I teach you another approach that we express directly the diameter as a function of Z. So how we do it? That here the diameter is 5.6 meter. So this is 5.6 and then it increases to maximum 12 meter. So we say that let us assume this is Z. Because I'm interested, I can calculate the diameter at any intermediate point. So in 10.4 meter, in this 10.4 meter, how much the change is occurring? 12 minus 5.6. This is the change occurring. When you simplify, this is equal to 5.6 plus 0.615 times Z. Okay. If you want to check that this equation is correct or not. So let's say I want to calculate what is the diameter here. let us calculate this value. So in here, when the diameter is 12 meter, what is Z? Z is 10.4. You put this as 10.4. When you put this 10.4, this cancel out with this 10.4, and this 5.6 cancel out minus 5.6. What we are left? Diameter is 12 meter, and this is 12 meter. So now we can express the diameter in this form. Now we have the area, which is pi by 4 d square. And now we get pi by 4 into 5.6 plus 0.615 z whole square. And if you simplify, we get A is equal to 0.297 into 9.1 plus z whole square. And you can see that this equation, this is essentially the same as we get this equation. You can see here, this is same as this. So any approach you want to follow, convenient to you, you can follow and you can get this answer.